Section 9.2, Test about a population proportion. In this section, we're going to check conditions for carrying out a test about a population proportion and conduct a significance test about a population proportion. In Section 9.1, we focused on the reasoning of a significance test, and now we're going to focus more on the mechanics of how to carry out a test. In Section 9.2, we will carry out both one-sided and two-sided tests for proportions. Recall our basketball player who claimed to be an 80% free throw shooter. In a simple random sample of 50 free throws, he made 32. His sample proportion of shots made, 32 divided by 50, which is 0.64, is much lower than what he is claiming. Does it provide convincing evidence, though, against his claim? The parameter for this example is the actual proportion of free throws the shooter makes in the long run, and his hypotheses are the null hypothesis of p is equal to 0.80 and the alternative value of p is less than 0.80. We need to remember to check assumptions and conditions before we continue. Remember in Chapter 8, we started talking about the conditions dealing with proportions. You have to have randomness, normality, and independence. So for this example, there is a random sample. It can be considered a simple random sample that's stated in the problem. Normality, making sure I can do my normal calculations. I take n times p and n times 1 minus p and make sure both are at least 10. And they are, so the normal condition is met. Independence, we're going to consider this a simulation when we did this, and therefore one simulation does not affect the next, so we do not need to worry about checking the population 10% condition. If the null hypothesis, p is equal to 0.80, is true, then the player's sample proportion of made free throws in any simple random sample of 50 shots would vary according to an approximately normally sampling distribution with a mean of 0.80 and a standard deviation that would equal the square root of p times 1 minus p divided by n. For this example, it would equal 0.0566. Here is a graph of that sampling distribution. The name of the test that we are going to perform is a one-sample z-test for proportions. After we name the test, we want to come up with the test statistic and obtain a p-value. A significance test uses sample data to measure the strength of evidence against the null hypothesis. Here are some principles that apply to most tests. First, the test compares a statistic calculated from a sample data with a value of the parameter stated by the null hypothesis. Values of a statistic far away from the null parameter in the direction specified by the alternative will give evidence against the null hypothesis. And therefore, the farther away, the more likely you are to reject the null hypothesis. How do we determine how far away we are? Well, we look at a test statistic. A test statistic measures how far a sample statistic diverges from what we would expect if the null hypothesis were true in standardized units. That is, the test statistic will equal the statistic minus the parameter divided by the standard deviation of the statistic. So for our example, the test statistic would be a z-score, and it would be p hat minus p divided by the standard deviation of the sampling statistic, which gives us a z-score of negative 2.83. If I look at the graph at the top, that's my normal sampling distribution. My graph below looks identical, and it is the standard normal distribution for this example. And what I need to do next is obtain my p-value by finding the probability that the z-score would be less than this negative 2.83. In calculating the probability that z is less than negative 2.83, I obtain a p-value of 0.0023. So, if the null hypothesis were true, the player makes 80% of his free throws in the long run, there's only about a 2 in 1,000 chance that the player would make as few as 32 out of 50 shots. Remember, if the p-value is low, the null must go. So here are the steps, again, in carrying out our z-test for proportions. First, you need to define the parameter of interest. Next, state the hypotheses. Check your conditions for the test. Name the method that you're using. Obtain or find a test statistic. And obtain a p-value. With that p-value, then, you're going to interpret the results of your p-value in context of the problem to decide whether you're going to reject or fail to reject the null hypothesis. When the conditions are met, the normal, random, and independent, the sampling distribution of p hat will be approximately normal with a mean of p and a standard deviation of the square root of p times 1 minus p divided by n. When performing a significance test, however, the null hypothesis specifies a certain value for p, which we will now change and call p naught, to match the sub-zero for the null hypothesis. We assume that this value is correct when performing our calculations. The z-statistic has an approximately normal distribution when h naught is true. P-values, therefore, come from a standard normal distribution. Here is a summary of the details for a one-sample z-test for proportions. I must take a simple random sample of size n from a large population that contains an unknown proportion p of successes. To test the hypothesis, p is equal to p naught, compute the z-statistic, z is equal to p hat minus p naught, that should have a 0 there, divided by the square root of p naught times 1 minus p naught divided by n. This denominator is the standard deviation of your sampling distribution, and p naught is your mean of your sampling distribution. After I have my z-statistic, I find the p-value by calculating the probability of getting a z-statistic this large or larger in the direction that's specified by the alternative hypothesis. If p is greater than p naught is the alternative, it's a one-sided test and the proportion is above. If it's p is less than p naught, it's a one-sample z-test, and I'm finding the area below the z-score. And if it's not equal to, I actually have two areas that I need to concern myself with, one at the smaller end and one at the bigger end, a larger end, and that is a two-sided test. This test only works when my conditions are met and my n times p naught and n times 1 minus p naught are both at least 10, and the population is at least 10 times as large as my sample. Alright, let's take this and run through an example. Here's an example we talked about earlier with the potato chip producer. The potato chip producer has just received a truckload of potatoes from its main supplier. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck, and inspection reveals that 47 of these potatoes have blemishes. I want to carry out a significance test at the alpha is equal to 0.10 significance level. What should the producer conclude about the truckload of potatoes? First, my parameter of interest is the proportion of actual potatoes in the shipment with blemishes. My hypotheses are the null will be 0.08, and my alternative would be p is greater than 0.08. I'm concerned about the proportion being greater than 8%, and if that's the case, I'll send the shipment back. So that's my alternative. And I'm testing at the significance level of 0.10. I need to check my conditions next. It is random. The supervisor took a random sample of 500 potatoes from the shipment. Checking the normality so I can do my normal calculations. N times p naught, 500 times 0.08 is 40, and n times 1 minus p naught ends up being 460. Both of these values are greater than or equal to 10, so we have no problem in doing our normal calculations. Independence. Because we are sampling without replacement, we do need to check the 10% condition. It would seem reasonable to assume that there are at least 5,000 potatoes in the shipment. The name of the test again is a one-sample Z test for proportions. To obtain my test statistic, Z, I need to figure out what my p-hat value is to do that calculation. So once I know that p-hat is 47 divided by 500, or 0.094, my test statistic, which is a z-score, will be p-hat minus p-naught divided by the square root of p-naught times 1 minus p-naught divided by n. The sample proportion, 47 divided by 500, p-hat, is 0.094. P-naught is 0.08, and I plug that in where the p-naught is, and my sample was 500. When I calculate my z-statistic, it ends up being 1.15. To obtain the p-value, remember I'm worried about the proportion being greater than 0.08. So my calculation for the p-value is going to be the probability that z is greater than or equal to 1.15. Using table A or the normal calculation on your calculator, you get a value of 0.1251. In terms of the conclusion, since our p-value is 0.1251 and it is greater than the chosen significance level of 0.10, we fail to reject the null hypothesis. Remember, if the p-value is low, the null must go. Since the p-value is bigger than our alpha value, we don't reject the null hypothesis. In context, then, you would say, there is not sufficient evidence to conclude that the shipment contains more than 8% blemishes of potatoes. The producer will use this truckload of potatoes to make potato chips. This is a good example of a one-sided z-test for proportions. In future lessons, we will talk about doing a two-sided test for proportions.